Hi, everybody. Welcome to class. Let me go ahead and share my screen and we'll get started in a sec. Okay, well, why don't we go ahead and get started? So today we're going to be discussing neural networks, actually today and Thursday. So this is a really hot area in data science these days. So definitely we can't teach this course without talking about it a little bit. So I hope you'll find the discussion interesting and maybe it'll pique your curiosity for some further investigation. So neural networks can be used both for classification and regression problems. So this is in the context of supervised learning. And in particular, we'll discuss perceptrons and multi-layer perceptrons. Perceptrons are the building blocks that we construct these neural networks out of. And we'll discuss how to do neural networks with scikit-learn and also some of the details about how to train a neural network. So do check out the recommended readings, the hands-on machine learning with scikit-learn and TensorFlow. We'll be talking about TensorFlow on Thursday. And also the deep learning by Goodfellow, Bengio, and Corville. And the TensorFlow's got a number of tutorials, which will probably be helpful for Thursday. Okay, there's also some recommended videos that I think you may find helpful. And if you want to learn more, there's definitely some courses that go into this in more detail. You may be interested in taking 7960. Okay, so we'll start off with all of our data imports. Pretty much our standard stuff, plus now we are using these new functions today, this MLP classifier and MLP regressor function from the sklearn.neural network library. Okay. All right, so artificial neural networks were originally motivated by the brain, which is composed of a network of neurons. So each neuron receives a signal from multiple other neurons, does a computation, and then decides if and how to release more chemicals. And this very basic phenomenon can actually cause really complicated can actually result in the performance of very complicated tasks. So in a similar way, an artificial neural network is composed of neurons. In this case, a neuron, we mean a basic computational unit. And so although the setup was originally motivated by how the brain works, artificial neural networks really do not model the brain. So we've kind of diverged between the original name and this really doesn't have to do with modeling the brain, but they're both made of neurons. Okay, and like I said earlier, so these can be used for supervised learning tasks like classification and regression. And so after today, we'll be able to add that to our toolkit list. So for regression, linear regression, KNN, decision trees, and neural networks, and classification. Actually, I'm sorry, I should have updated that. We didn't have time to discuss logistic regression, but we have talked about KNN, decision trees, SVM, and neural networks now. Okay, so large-scale neural networks are really at the core of deep learning, and they're responsible for doing some pretty amazing classification and prediction tasks. Here are just a few examples, classifying billions of images with pretty high accuracy, for example, Google Images. They have really good performance for speech recognition. like Amazon's Alexa or Apple Siri, and also video recommendations, YouTube, etc. And they've even been responsible, so they built a deep neural network that was able to beat the world champion at the game of Go. So even surpassing the very best of human expertise in certain areas. Okay, but let's go into what it actually is. Okay, so a neural network is constructed from perceptrons. So the very simplest neural network you can think of as a perceptron, which was invented in the 50s by Frank Rosenblatt. And this is just a binary classifier. So it's a function that maps a set of n features, x1 through xn, to some binary output. So we can have some function f of x, say, which is 1 if the inner product of w and x plus b is greater than 0 and 0 otherwise. So this may look very familiar. This may remind you a lot of support vector machines back when we were discussing support vector machines, and we had our linear classifier written in a very similar way. So here, W is called the weights, and B is called the bias. Right, so this is very similar to the SVM setup. And a lot of times we like to write this out in a diagram. The deep learning literature is full of lots of diagrams, so we can visualize this as follows. We have our input vector here on the left. Let's say we have n features, x1 through xn, and then we choose weights, w, which will do an inner product of x and these weights. And here the bias is actually being represented by W0. So in terms of this notation up here, W0 would be a B, but in this diagram, they're kind of, adding that to the input and writing it all as a W. And then it gets mapped into some nonlinear function, generally denoted with a sigma. Okay. And so just like for our previous classification methods, we first train the network on data. So we want to find what is a good W and what is a good B, what are the right choices of these parameters W and B in order to get a good classification on the training data set. And then, just like before with our other methods, we can see how well the neural network performs on a test data set that was not used to train the data, right? So we have, training data set where we tune the W's and the B's, and then we test it on new data. Okay, and so this is just in its simplest form, a linear discriminator, like SVM, but we are going to sort of build on this to get something that's much more complicated that actually consists of multiple layers. Okay, so now let's discuss what's known as the multi-layer perceptron. So like the perceptron, a multi-layer perceptron is a function that maps input features, which I can call X. So I have input features to some target response variable Y. And here is a diagram of a multi-layer perceptron with 3 layers. So here is my input. So I've got a 3-dimensional input here. And then I map this to a hidden layer, which is 4-dimensional. The hidden layer could be bigger or smaller than the input layer, depending on the architecture. And then I map the hidden layer into the output layer, which here is 2-dimensional in this example. Okay, so here the dimension will be my number of features. Here the dimension will be my whatever my response variable is, or if I'm doing classification, the number of classes that I have. And then here, this hidden layer in the middle can have any dimension, and we'll see we can have any number of hidden layers. Okay, so here, each layer represents a function. So this is kind of really important to understand the basics of what's going on here. So just for this first example, let's look at the math that's happening. Okay, so here we have our three-dimensional input vector, right? X1, X2, X3. This is our input. We're going to multiply this three-dimensional vector by a 4x3 matrix. That's going to give us a four-dimensional vector, which we add to this four-dimensional vector. This is the bias. So we can think of all of this as some linear function on the input. And then we take that four-dimensional vector and we apply a non-linear function. This is called the activation function, and we'll talk about that in more detail later on. But we feed that four-dimensional vector into an activation function, which is applied entry-wise. And this is then the result that we get. These are the values of the hidden layer. So the hidden layer is now this four-dimensional vector, which you can visualize as these blue circles. Okay, so then you take the hidden layer, multiply it by this 2x4 matrix. You get a two-dimensional vector, add this two-dimensional bias. So you take another linear transformation of the hidden layer, and then you apply your activation function, your nonlinear function, to get the final two-dimensional output. Okay, and then if it's a classification problem, a lot of times you'll then follow the output layer with a softmax function. For example, let's say we have a data set consisting of dogs and cats, and what gets output here, it tends to be a big number if it's likely to be a dog, and this tends to be a big number if it's likely to be a cat. But we want to actually follow that up with a probability that's between 0 and 1. So the softmax will transform these numbers, which could be on any scale, into actual like class probabilities. And then say, okay, it's a 90% probability that it's a dog, 10% probability that it's a cat. Okay. Okay, so to train the network, that means we have to find the best matrices, right? In this example, we have to find the best AH and the best AO, as well as, I'm not sure why we used A here instead of W, but that's fine, as well as the best biases, BH and BO for the data. So in this case, it's a relatively simple network. So we've got a 3x4 matrix, 4x2 matrix, and then a four-dimensional vector, two-dimensional vector. All together, you can count up all of these parameters that have to be chosen, and it's 26 parameters, which is a lot, okay? That actually is quite a lot. We've been doing other, I mean, that's nothing compared to a typical neural network implementation, but compared to some of the other methods that we've looked at, that have, 2 or 3 parameters. It's a lot of things to play with. Okay, any questions on that so far? This is just kind of the basic nuts and bolts. Okay, well, do feel free to interrupt with questions or to put them into the chat. I will say there's lots of network architectures out there. So there's lots of different ways to design these things. We've been looking at kind of the most basic setup for what would be called a feed-forward neural network. Notice all of these arrows are going forward. You never have output that kind of loops back around to the beginning of the network. But there's a lot of variations. And so, for example, here you can just see there's a lot of stuff here, and I won't talk about all of it, but I can maybe give you a few highlights. Recurrent neural networks are used a lot for input data that's a sequence, so like a temporal input data, or maybe like when you're doing text data processing and the words have an order. That might be useful. So in a recurrent neural network, you'll have, some kind of sequence with like a temporal dependence, and you'll have stuff that kind of feeds in, unlike the feed forward neural network. With an autoencoder, the goal here often is to find a good way to do dimension reduction. So you kind of take your input and you kind of squeeze it into a narrow hidden layer in the middle. And the idea is that these would be good features to do dimension reduction. Also, convolutional neural networks are really popular for image processing. So that's big. You think about having some filter that you then kind of scan over your data. And these actually are cheaper to implement than a fully connected feed forward network. So that has a number of advantages in terms of being computationally efficient. Okay. Some of these I'm not familiar with, but there's a lot on here. In a generative adversarial network, or again, it's trying to fool a classifier. So it's trying to generate examples that will fool a classifier. And then that sort of helps it learn how to, helps it sort of train a really good classifier. Okay, but anyway, the most important thing about all of these networks is there's an input layer, typically drawn on the left-hand side, and an output layer, typically drawn on the right-hand side, and the middle layers are called hidden layers. And when you may have heard the term deep neural network or deep learning, and a deep neural network is simply a neural network with a lot of hidden layers. Okay, and so in all of these designs, there are parameters that have to be learned. You have a weight matrix and bias vector that needs to be trained. And so consequently, training these networks is much harder, a much harder thing than we've needed to do for our previous supervised learning methods. So we need a lot of data, and we need a lot of computational power. Okay, so for example, ImageNet is a test data set for visual object recognition. So this data set is very large. It's 14 million images in approximately 20,000 categories. So for most categories, each category would have a few hundred images. The categories could be balloon, strawberry, things like that. But this is an enormous number of categories. So your output layer here would be a 20,000 dimensional vector, where you have one dimension for each category. And so here we can see how the performance on this data set improved over time. In 2010, which was the first year that they did this competition on who could get the best performance on the ImageNet data set, every team got at least 25% wrong. And then in 2012, the first team appeared that used deep learning, and you can see how much they improved over the other teams. And that just sort of started the beginning of kind of an explosion of deep learning tools in this area, and you can see that in the coming years, much higher and higher accuracies were achieved until in 2017. They got, most of the teams got less than 5% wrong, and the winning team was implemented a deep neural network with 154 layers and 10 to the 8th parameters overall. Okay, so let's talk a little bit about how to implement a basic neural network in scikit-learn. So scikit-learn has a neural network library that we can use. However, the library offers the following warning, which is that the implementation is not intended for large-scale applications. I do think it's a great learning tool. When you're first getting exposed to this area, it's great to get familiar with and to play with, but it does not offer GPU support. And so for faster GPU-based implementations and for frameworks with more flexibility in terms of architecture design, we may need to use something else. Okay, but that's what we're going to start in scikit-learn today and get familiar with a few of the basics of neural networks. And specifically, it has a few different functions: the perceptron function, and then the multi-layer perceptron MLP classifier, and multi-layer perceptron MLP regressor. So just depending on what type of supervised learning you're doing. So let's start off taking a look at MLP classifier for the 2Moons dataset. So first we can generate our data with our handy little make moons function. And then here, we've done this lots of times. We're going to plot the data so we see our red moon and our blue moon. And let's now see how we can use a neural network to try to learn a classification rule for the moons. So here's the basic syntax. So we're going to call the MLP classifier function. There is a default for this, but here we're specifying the hidden layer sizes, 3, 3, 3. Okay, so our input data is 2-dimensional, and then it's going to feed into 3 3-dimensional hidden layers. Then the output is actually going to be 1-dimensional because it's going to be a binary classification rule, blue or red. Here we specify the maximum number of iterations. Of course, it's kind of good to make this a large number because you want it to converge. You want the training to converge, but if it's just not, but it could make it run for a very long time if you make this, if it's not going to converge and you haven't put in a good cutoff here, then it may just kind of churn and churn. And we'll talk about some of these other parameters in a little bit. But once we define our model, then we can call model.fit with our data and our labels. And then we can see each iteration as it's training. Remember what it's doing. It's finding the best W's and B's to use in this classification. And eventually it converges. Again, we'll talk about that in a little bit. But let's take a look at the classifier that it found. So here we can once again plot the data colored by class, and then we can plot the predictions made by the neural net. So this is again defining a grid of points, a mesh, and just like we've been doing in a lot of our lectures. And then we can apply the predict function to see what the MLP classifier result would predict on that mesh. and then do the contour plot to color it in. And this is what we get. So here we see the red region is where the MLP classifier would predict it to be in the red class, and this region where it would predict it to be in the blue class. And so you do see a nice nonlinear boundary that it finds, even without, this is not a very deep neural net. Okay, and so let's take a look at a few more of the specifics here. So how many iterations? Yeah, you can see it took 45 iterations to converge. We said a max of 1,000, but it only took 45 to converge. And so we can see after 45 iterations, this is the loss. You can access the value of the loss, which we'll talk a little bit more about later in the lecture, from this model.loss underscore. And also the coefficients are stored in model.coefs underscore, and the biases or the intercepts in model.intercepts. Okay, and so let's take a look at all of these things. First, it's outputting the shape of the coefficients, and then it's actually outputting the model coefficients themselves and the intercepts. If I can, let me see if I can draw this, right? So remember, we've got a two-dimensional input because this is two-dimensional data. We specified we're doing 3 hidden layers, which are each consisting of 3 neurons apiece. And then we're outputting a one-dimensional output because it's a classification problem. And so you can kind of visualize it in the following way. Right, so this neuron is going to feed into all of those neurons. This neuron is going to feed into all of these guys. And similarly here. Okay, I won't draw all of these, but let me just make sure that everybody is following the shape here. So, okay, right. So in the beginning, we go from 2 dimensions to 3 dimensions. And so you can see how the shape of this matrix is 2 by 3. Then we go from 3 dimensions to 3 dimensions. So this is 3 by 3. So you can see how these sizes kind of line up. Okay.
I have a question.
Yeah, go ahead.
So you specified doing 1,000 iterations. What does how does the second iteration differ from the first? What is there like a random seed that changes something and sees how good it is, or what does an iteration look like?
Yeah, okay, right, exactly. So that's still a little bit mysterious right now. I'll just kind of cheat and go ahead real quick so I can kind of answer your question. What's happening, and what we'll discuss in a minute, is that we have a loss function. Remember, we're trying to find the best weights. We're trying to find the best weights and biases to make the prediction. So we're trying to find the best W's. These are just randomly initialized. And then you define a loss function, which sort of sees, okay, if I make a prediction based on those W's, how well does it match up with my actual Y's in the data? So you'll get a Y hat predicted by the network and a Y that's actually your data. And you look and see how big the loss is, like how messed up your prediction is. And then you implement some kind of optimization algorithm, something like a gradient descent algorithm, where you then differentiate this loss and you take a step in the direction of the gradient, and then you get to a smaller loss by doing that. Then you repeat, right? So at each iteration, you're changing the weights. At each iteration, you're changing the weights a little bit in a way that decreases the loss, that makes the y hats match up better with the y's. So if we go back up here, we can see that the loss should be decreasing. Yeah, we can see maybe not always decreasing, but generally decreasing until it kind of gets smaller and smaller and smaller until eventually it can't find a direction where it really decreases by taking a step in any direction. And so that's when it will say, okay, that's as good as we can do, and it converges. Does that help?
Yeah, no, that does. And that leads me to one more.
Yeah.
So how you were showing neural networks earlier that incorporate kind of the output back to the beginning.
Right.
So I guess, how does that differ from that process?
So it's going to be kind of a similar idea of you define a loss function, and then you have to optimize to find the best weights. But but now some of those values will feed back, like back into the layers. The implementation then gets a bit more complicated because you have, more complicated dependencies. So I probably won't go into a lot of specifics there. Actually, I'm not an expert on those things either, but the basic idea is the same, but the structure is more complicated for those types of networks, and you would have to take that into account.
Okay, thank you.
Mm-hmm. Any other questions? These are good questions. Okay, I'll go ahead and clear my little drawing. Okay, so we saw the picture and we were kind of going into the details here of why it's this size. And here we're printing all of the model parameters with this model.getParams function. And so you may notice there is a lot going on. We're going to talk about some of this. We're not going to have time to talk about all of this. And there is a number of things that are sort of defined with a default that you don't have to specify to run the algorithm. But we'll try to discuss the ones that make a big difference so you can get an idea of what all of these different parameters are and how they affect the results. Okay, so what are some of the most important things to be aware of? Well, first of all, the hidden layer sizes. So these are, first of all, network architecture parameters. We specified this, right? And when we applied it to the two moons, we had a tuple that was 3, 3, 3. So we were doing 3 hidden layers, each with 3 neurons. The default is to do 100 neurons, but you can specify it to be anything you want. And there's a lot of expertise. I mean, it's hard to know what the best design is. That's definitely something that you can play with. Do you want to make really deep network? Do you want to make it more shallow but with a lot more neurons per layer? Different things to play with. And then there's the activation function, which is that sigma function that we back up here when we were defining what we were doing in this multi-layer perceptron, right? We take a linear transformation of the input, but then we apply some nonlinear function sigma called the activation function. We apply this entry-wise to each element of the vector. And so your choices for this activation function are the identity. Really, that means it doesn't do anything. That means it doesn't apply a nonlinear function. So that I would not really call a neural network. So that's just more like a composition of linear functions. But they do have that functionality. Actually, to do a neural network, the most popular one is ReLU, the rectified linear unit function. So this is where sigma max is defined as the maximum between 0 and x, and that is also the default for Python. But some other options are the logistic function and the hyperbolic tangent function. Both of those kind of have like an S shape where they kind of, they kind of grow and then level off. We'll see some pictures here in a second. Okay, and then this alpha parameter is a regularization parameter, which is used to define the loss function. And so we'll go over, we'll see that a little bit later when we look at the loss function. Then there's also lots of parameters related to the optimization procedure itself. There's 3 different solvers. So remember, this is the optimization. We have a loss function which measures how well the predictions of the neural network match up with our training data. And we want to minimize it. We want to change the W's in order to get a small value of the loss function. And there's different algorithms for this. LBFGS is an option, which is in the family of quasi-Newton methods. There's stochastic gradient descent. And there's also ADAM, which is kind of a clever variation on stochastic gradient descent. So these are, gradient-based optimizers. You're trying to take a step in the direction of the negative gradient, but there's kind of lots of different ways of implementing that. And for stochastic gradient descent, you don't want to estimate your gradient using all of the data because that would be way too expensive. So you're taking a random sample of your data, using that to estimate the gradient. Okay, and then we talked a little bit about the maximum number of iterations. The default is 200, but you can adjust that. And yeah, so if you really, really, really want it to converge, set that to a big number. If you want to give up, if it's taking too long and try something else, then set it to a smaller number. The random state parameter is in order to, if you want reproducible results, so you want to be able to run it again and get the exact same random seeds, and so the exact same initialization for the W's, and thus the exact same performance of the optimization procedure, you can just set this to some integer. And then this tolerance parameter, basically the optimization stops when there's not much change, right? So when you've stopped really being able to decrease your loss much by stepping in a gradient direction. But this kind of controls how granular that decision is. So when the loss or score is not improving by at least this amount for 2 consecutive iterations, then it'll consider the algorithm to have converged. And then this option just tells you if you want to actually see the iterations, so you want to see how much the loss decreases in each iteration, then you can set verbose to true. Otherwise, if you don't want to see all of the details, you set it to false. Okay, so sorry, that's kind of a lot of different inputs, but that's not even all of them. You can start to see that there's a lot of things that you can play with here. But let's take a look. Actually, let's take our break. Since it's 1:05 now, why don't we go ahead and take our 5-minute break, and then we'll come back and we'll look in more details about the activation function and look at some more examples, etc. Okay, so We'll break and I'll see you back at 1:10. All right, welcome back. Let's pick it back up. So yeah, let's discuss a little bit about the activation function, the sigma x. So some common choices and ones that you can do in Python are the hyperbolic tangent, the logistic function, and the rectified linear unit or ReLU. So in the Moons implementation we used the default, which is the ReLU. And let's just take a look so you can see what these functions look like. So here, the logistic function, if you want to think of that as some function of z, it's defined as 1 over 1 plus e to the minus z. And then here's our ReLU. And then here's a function that just takes the derivative of any function with a difference quotient. And then we can take a look at what these functions look like. So here's a plot of the ReLU in purple, right? So this is 0 for negative numbers, and then becomes the line y equals x for positive numbers. And then here's our logistic function, which you can see is this kind of S-shaped curve. And then all similarly for the hyperbolic tangent, has a similar shape to the logistic function, also kind of an S-shaped curve, but going to -1 down here. And if you look at the derivatives of all of these functions, you can see ReLU is not differentiable at 0, but everywhere else it's differentiable. And over here it's 0 and then it's 1. And then for the logistic and the hyperbolic tangent, we have kind of a bell-shaped derivative. So I will say that one reason that ReLU is very popular is that if you think about what happens for larger and larger x values, the derivative stays equal to 1. On the other hand, for the logistic function and the hyperbolic tangent, what happens is you get out into these bigger numbers is a phenomenon known as gradient saturation. The gradient converges to 0, and that is actually difficult for, that can cause problems for gradient-based optimization. So the ReLU in some ways plays more nicely with these gradient-based optimization methods than some of these other activation functions where you have this gradient saturation where the derivative converges to 0. Okay, I think, so we've got an exercise here, which I'm hoping we'll have time to come back to, a couple exercises in the lecture, but maybe we'll sort of finish our discussion, and then hopefully in the last 5 or 10 minutes, you guys can play with some of these exercises and play around with the inputs and see if you can get some better results. Okay, so now let's talk a little bit about training the neural network after you've decided on which activation function you're going to use. So we talked about this a little bit, but it's important to understand what's going on here. We're training a loss function, and you should think of this loss function as a function of W. So really, the y-hats are uniquely determined by the W on the training data. So you might even think of this not so much as a function of the y-hats, but as a function of the W's and the Y's that you're trying to match, because the W determines the y-hats. And here by capital W, I mean all of the model parameters. So these are all of the matrices, all of the weight matrices, and also all of the biases. I'm just putting all together in this one notation of W. But generally, you measure the loss function in this way. So you might take the average loss, where the loss is computed with some function f that compares the predicted value y hat, right? Y hat is predicted based on xi and based on the parameters that were chosen for the neural network. And we want to see how closely that matches up with what we observe in our training data. So this is exactly a data fit term, but then this second term is a regularization term, where an alpha is a regularization parameter. If we choose, alpha to be large, we're trying to minimize this loss function. That will try to keep the L2 norm of the weights small, so we can't let the size of the weights just keep growing and growing and growing. But if alpha is really small, then you might see that happen. You might see some really big weights in your network. Okay, so as I think we kind of said this, the yi are the true labels. The yi hats are the labels predicted by the neural networks. W, all the parameters. F, some way of measuring loss, and alpha, your regularization parameter. Yeah. Okay, and then, so usually the weights are initialized randomly. So you just, maybe they're a random Gaussian or something like that. Then the loss function is minimized by repeatedly updating the weights. And the details of that depend on the specific optimization algorithm that you use. But in general, for gradient-based descent methods, and for this gradient descent method, the basic idea is that you're going to differentiate the loss with respect to W. So you take the gradient with respect to W of the loss, and then you're going to take a step in the direction of the negative gradient. So you're going to update W as W minus epsilon, where epsilon is a step size, times the gradient with respect to W of the loss. Okay, and you're going to stop this process either when you reach the maximum number of iterations, or before that, if your algorithm converges, then and your loss is not changing. Okay, and how this gradient is actually computed, it's actually computed in a simple way. It basically utilizes the chain rule from calculus. So this is a very simple idea. It can be a very long chain rule if you have a very deep network. And so there is a really clever way of organizing this calculation to make it easy and fast. And this method is called backpropagation. So we're not going to have time to really go into the details of that right now, but just know this is kind of a clever implementation of the chain rule that allows you to compute the gradients quickly. Okay. All right, so let's take a look now at the effect of varying the optimization algorithm that we use to train the network. So here, we're going to try a number of different things. So these first, 6 methods are all stochastic gradient descent, but with slightly different parameters. So, so this learning rate parameter is related to the epsilon here. So in general, if you have a large epsilon, you have a high learning rate, you're taking big steps. That's nice because you might converge quickly, but you might also get yourself into trouble because you're moving too quickly. A small epsilon will, be a slower learning rate. It may take a little longer to converge, but it may work a little better in the end. There's lots of learning strategies where you start off with a larger epsilon in the beginning of your training. And then as you increase your iteration, usually you decrease the epsilon. So you get like, use a smaller step size later in the optimization. But there's a whole lot of literature on this, a lot of different strategies. But that's kind of what related to this learning rate parameter. So a constant learning rate, just kind of keeps this epsilon fixed throughout the course of the optimization. But there's some other options here, inverse scaling. So that's going to make it, smaller as you increase the number of iterations. And you can also, there's also whether you want to include momentum or not for the stochastic gradient descent. Anyway, we won't go over all of the details, but let's just take a look at the performance. So here we have some code that actually applies all of these different training models to the data and then computes the loss. And if we take a look at that, so we see this is on the IRIS data set. Well, actually, sorry, maybe I should go over this a little bit more carefully. We're going to look at this on a collection of data sets, which is the IRIS data set and the digits data set. And what are the other ones that we're doing? We're doing the IRIS and digits and the moons and also the circles. So on those 4 different data sets. And here's the output, and then also a plot of the output is probably a little bit more helpful to look at these plots here. In red, you can think of this as maybe kind of a baseline, because the red is stochastic gradient descent with a constant learning rate, which is kind of the simplest implementation. And you can see that that's doing all right, but ADAM, which is a newer method, is actually usually beating that by a good bit. So ADAM's doing better here and really well on the circles, really well on the moons, where these other methods don't even make it down to this low of a loss. ADAM has a little comeback here on the moons. So ADAM is working very well, and also some of the stochastic gradient implementations that incorporated momentum. Okay, so if you want some more advice on optimization, you can check out that page. And according to this resource, they note that the LBFGS tends to converge faster and has better solutions on small data sets, but it may not be as well suited for large data sets. For large data sets, you probably need to do ADAM. ADAM is very robust, or stochastic gradient descent with momentum also works very well. Okay. Any questions on that? Okay, I feel like I forgot to show the effect of the alpha. Where I feel like we forgot. Okay, 1 sec. No. Maybe that's coming later. Okay, sorry, never mind. We'll see if something I thought I was going to talk about that now I don't see, but maybe it's coming later. Okay, let's take a look at another example here. This is the breast cancer data set. So we can load the data and then print cancer.keys, this will tell us everything that's contained in this data set. So that will be really helpful. So when we do that, we see what do we have here? We have the following keys. We have data. Those are the actual features. We have target, which is the labels, frame, target names, description, that may be helpful for understanding what the data is, feature names, file name, etc. Okay, so then if we call, now that we know that description is one of these keys, we can print this and get a little description of the data. So for this data set, we have 569 data points. Each data point is 30-dimensional. It has 30-dimensional feature vector associated with it. And basically, the features are of the following attributes: radius, texture, perimeter, area, smoothness, compactness, all of these things. And then I think what they did is they looked at, for each of these features, their data points were images of these tumors, and they had like images of these different cells in the tumors. They identified the cells and then computed radius, texture, area, all of those things in each image. And then as the recorded features, they recorded the mean, the standard error, and the worst or the largest 3 values for each of those features. So even though there's only like 10 listed here, there's really 30, because for each of those, they have mean, standard error, and worst. Okay, and so here you can just see then what all of those 30 features are. And then they have a label which corresponds to whether the tumor was malignant or benign. Okay, and then I think we can just skip the rest of that. Okay, so let's try it. So let's try this MLP classifier, and let's try 3 hidden layers again, say each of size 30. So here we're not really varying the dimension. We're starting off with 30 dimensions and then just keeping it fixed in the hidden layers. And we'll add this to make it reproducible. Okay, so this is our model, and then we can fit it to our training data, and then we can predict on our test data, and we can see how well we do here by looking at a confusion matrix between the test data set labels and our predicted labels. And we see that actually it does very well. So on the training data, which is a small, I don't know, what is that, maybe 20% of the data, something like that. It looks like it's only misclassifying 1 point. Okay. And then here is I guess the examples that we've seen so far. We have been looking at binary classification. Here's an example on the IMNIS data set. So this is helpful for a little bit of a look at an example with a higher dimensional output. And let's see how we can train a multi-layer perceptron on the IMNIS data set. So this is a larger version of the data set than we have used in previous classes. This is 70,000 data points and 28 by 28 pixel images for each one, but again, 10 classes. So I added this data set manually. I just downloaded it from the website and added it into the folder for today's lecture, but it is large, so I zipped it. So if you're following along, just unzip it before you try running this code. And then we can load with this function, which is handy for loading MATLAB files. If you've done a lot of work in MATLAB, you might be interested in using that. So that's this io.loadmat on the MNIST data. And once again, we can print out what these what the type is here. And we can see that this is a dictionary, and we print out the keys. We can see that we have the data stored and we have the label stored. So we can extract that as follows. You know, we're going to define our X by extracting the data, normalizing it so that it's on a scale between 0 and 1. We're dividing by this 255, and then also extracting the labels. And then a little bit of formatting that's necessary. You just transpose it and ravel it so that it's in the right syntax to feed into the MLP classifier. And so here, once again, we can now define, let's say we do 2 hidden layers, each with 100 neurons, so that it doesn't take too terribly long to train. And then we can set the parameters, maybe 400 for our max iteration, and using Atom, which we've seen works pretty well. And let's see how well we can do. Okay, so on the MNIST data set, you can see that it's really, the loss function is converging pretty quickly and actually converges in 40 iterations. And on the training set, it gets a score of 1. So this is like 100% accuracy on the training set, and on the test set, it's getting a score of 98. And you can see from the confusion matrix, yeah, that it's doing very well. Okay, so I don't know if you remember the accuracies that we were getting back when we were doing clustering, but they weren't 98. Okay, so they were much lower. So this is pretty impressive performance. Okay, so I'd like to come back to this. So let me just, in the last few minutes, let me go over one last example, because we haven't looked at one that does regression yet. And then we'll hopefully come back and we can play with whether we can get better performance by adjusting this. But so far, we've been looking at this MLP classifier function, but you can also do regression, okay? So neural networks are used a lot for classification, but also for regression. And so here we can take a look at this California housing data set. And this is a data set that has a lot of well, actually, we'll get down to the description. First, we'll load the data. And then once again, we can look at the keys that are present here. Once again, we have a description, which is helpful. So when we print that out, we can see what the features are. We've got about 20,000 data points, 8 features per data point. And we're looking at median income in a block. A block is like a small geographic zone. We're looking at median income, median house age, average number of rooms. And what we're trying to predict is what the median home price in that geographic unit is. Okay, so that's the goal. So once again, we define our features and our labels, and then we can do, train, test, split, reserve 20% of the data for testing. And then we want to scale the data. Again, scaling the data for this data set is very important, because these are all kind of different features. These are not measured in the same units on the same scale. So we need to make sure to scale the data. Okay, but then after we've done that, we can compare, first of all, with what we would get with just a standard linear regression in scikit-learn. So the linear regression function that we learned back when we were doing linear regression, we can define this model, and there are very few parameters that you would need in order to do this. So let's take a look. If you print the parameters that you need for linear regression, then you can see, well, actually, when you actually fit the data, fit the training data, and then print the intercept and the coefficient, what are you doing in this linear regression model? Well, you're doing y equals mx plus b in its simplest form. Here we have an eight-dimensional vector that are linear coefficients on all of the 8 features. And then we have an intercept here. So we have a total of 9 parameters for this standard linear regression model. And then how well are we doing? Well, here's the score. Score 1 is good. What it's doing here in the context of regression is computing the R-squared value between the x, the R-squared value for the linear regression. In this case, it's 0.59, which is okay, but that's not great. And then we can pair with what we can get with a deep neural, well, this is not deep, but with a neural net. Here we're going to do 2 hidden layers, each with 8 neurons, and once again use Adam. And so we fit the data and then print what the score is associated with this model. Here, the score is going to be the R-squared value between I think the y's and the y hats. So 1 will be good, and we get a score of 0.758. So we do see a good bit of improvement here. Granted, we're using a lot more parameters to define our model, but the performance is much better. Okay, so yeah, I mean, really not a whole lot new to say in that example. Just wanted to do one that does regression instead of classification, but a lot of the logistics there are the same. It's just the MLP regressor instead of the MLP classifier. Oh, and it looks like here it actually didn't converge. So if this happens, we could try to see if we can get better performance by increasing the number of iterations. Let's see. So let's try it. Yeah, so now we converged, but actually things didn't really improve a whole lot in terms of score. But anyway, at least it's nice to know that that's as good as you can do with that model. Okay, so I just wanted to mention another resource if you're interested in learning more about neural networks, which is Neural Networks Demystified. This is a good sequence of 7 videos on various topics like the architecture of the network, forward propagation, gradient descent, back propagation. So check those out if you're interested in learning more about how to train neural networks. Okay, and then also, like we mentioned kind of in the beginning of class, this is a great tool for getting started with neural networks and learning some of the basics, but it's not intended for large scale applications, but there are many other packages that have more advanced implementations of neural networks. And here's a partial list that you can look through. We'll talk about TensorFlow in this class. Okay, and then that's what we'll do on Thursday. Okay, so why don't we take a look then? Well, first, see if there are any questions, and then I'm curious if anybody tried the exercise. Did anybody improve the performance on MNIST by changing the architecture or any of the optimization parameters? Did anybody find something that worked better? Well, one thing that might be kind of interesting to play with is adjusting the hidden layer size. Maybe you keep like your number of neurons fixed, but maybe you change how they're distributed. So here we have a hidden layer with 100 and 100. We have 200 layers altogether. So let's see what happens if we do a deeper layer. Same number of neurons, but now we have 4 hidden layers spread across 4 hidden layers instead of 5. This is going to take longer, right? Because there's more parameters here, and it'll be a little bit more expensive to compute gradients. A lot of times you can get a more complicated classifier by using a deep network, but it does get more and more expensive to do. So let's see if this is going to converge. But yeah, in the meantime, any other questions or any other, here we go. Interestingly enough, that made it worse. So that actually made the performance worse. Who knew? Okay, so no one else try something that improved performance? Okay, well, maybe you can play with that, and then you can report back on Thursday and see if anybody finds something that improves the score on the test set over the 0.98 that we started with. All right, well, why don't we call it a day, and we'll pick this back up on Thursday. Hope you guys are having a good week, and see you then.
Thank you.
Thanks.